Here. Today, I am excited to introduce our speaker for this week's MLFL. Uh, it's Silvia Sellan. Sylvia is currently a postdoc at MIT and an incoming assistant professor at Columbia University, where she conducts research on problems in the intersection of computer graphics and geometry processing, including the title of today's topic. Sylvia obtained her PhD from the University of Toronto, where she was a Vanier Doctoral Scholar, an Adobe Research Fellow, and the winner of the 2021 University of Toronto Dean's Doctoral Excellence Scholarship. In the past, she has interned at Adobe Research and the Fields Institute of Mathematics, and is also a founder and organizer of the Toronto Geometry Colloquium and a member of WiGRAPH. So without further ado, let's all welcome Silvia to MLFL. All yours,
Thank
Silvia.
you. Thank you. I'll start by saying that I've been having this horrible cold for like 3 days now. So please forgive me if I have to take breaks in the middle of the talk, but I'm going to try to do my best. Um, I am here to talk about some of the work I've done in computer graphics and geometry processing, and maybe more excitingly, some of the work that I plan my new lab at Columbia to do over the next few years. I didn't know it was pronounced MLFL. So that's a fun way of pronouncing it. I am the and friends part in the machine learning and friends, but hopefully I'm gonna keep this talk mostly at a high level, and you're gonna learn about something that I've done in what I like to think of as a very neighboring field to machine learning and computer vision and things like that. So anyway, I work in computer graphics. So when I tell you computer graphics, the first thing that probably comes to mind is some of these film, TV, video game, social media companies that are pictured here that many of us use every day. And you wouldn't be wrong for thinking that when I say computer graphics. This entertainment industry has been the dominant application realm for our field, and the vast majority of the research in our field has focused on serving the needs of these industries. Which is definitely not a bad thing, right? In serving the needs of these industries, our field has done amazing things. We've designed efficient 3D modeling algorithms that allow artists to create beautiful digital assets that can be used in movies. We've designed simulation algorithms that are so efficient that can compute how a complex object distracts when receiving an impact in less than the hundredth of a second that it takes a video game to render the next frame in a simulation, right? That's just how efficient we are now. And we haven't just made things prettier and faster. As a field, we've also dared tackle what seem like fundamental, seemingly impossible problems, like how do you fool someone into exploring a scene in virtual reality while moving inside of a much smaller space in the real world? I have nothing to do with this work, but I will always like bringing it up because I think it's an example of the kind of impossible looking problems that we can solve when we put our minds to it in computer graphics. Uh, these amazing advances have made it so that you and I can enjoy the latest video game or watch the latest movie. They have democratized storytelling, right? Which has been transformative in our society by expanding the kinds of stories that can be told and the kind of people that can tell stories. So we shouldn't discard these advances just because they've been done in service of the entertainment industry. However, this focus has meant that we have not paid as much attention to other equally vital computer graphics applications like medicine, robotics, engineering, journalism, and many others. Indeed, when researchers in these fields have needs that perfectly align with computer graphics, they're forced to repurposing algorithms that were initially designed for entertainment applications. Now, I think this is pretty inefficient, and it can even be dangerous sometimes, since these are different, very different application realms and different application realms that have different algorithmic priorities, right? This is not a very controversial statement. The trade-off between speed and precision is obviously different for a video game developer than it is for a surgeon, right? And algorithmic explainability is less important for a visual effects artist than it is for a journalist. My research tries to avoid this and instead build the theoretical tools that address the needs in these other industries. So this is what I do and what I have done throughout my research career. So today I'm going to show you some examples of this and slowly build up to what I think is a general purpose framework to extend graphics to these safety critical applications, which is reinterpreting graphics tasks from a statistical perspective, letting us incorporate priors and quantify the uncertainty of our algorithms. And this is the sort of movement that I have called stochastic computer graphics that will hopefully become clear what I mean towards the end of the talk. But first, let's think of some examples of situations where repurposing tools designed for entertainment doesn't just work, and we instead need to address the needs of specific applications. So let me give you an example. Let's think of how 3D shapes are designed, a process that we in graphics call modeling. In the entertainment industry, the priority is generating new, diverse, and rich assets that are cheap for an artist to create. So it makes sense that most of our research focuses on free, easy, creative modeling algorithms. I'm guilty of this too, by the way. Some of my earliest works in our field was precisely for one of those companies whose logos I put up there, so no hard feelings there. However, this set of priorities is different in applications like manufacturing, where you want assets that satisfy a specific function that can be easily fabricated, and perhaps even at a massive scale. If we repurpose the tools that are traditional in entertainment applications, we will end up with beautiful 3D assets that look great for a movie or a video game, but either cannot be fabricated or are useless for the specific application that we want them for. Instead, I've designed task-aware, fabrication-aware algorithms that directly address these needs. I'm not going to get into the details of this, but mostly I've done this by looking at the modeling process from a statistical lens and reinterpreting these tasks and fabrication constraints as priors that are imposed on the modeling process. For example, this beautifully patriotic maple leaf. I did my PhD in Canada, so I have to add a maple leaf in every talk from now on. It's a great shape for a flag design, but if we try to cut it with a machine with a round end mill, it'll be impossible to generate since the end mill won't be able to reach those very concave crevices in the shape. So one of our earliest works was about modifying the design process to impose a prior on the object's curvature so that it can be fabricated with this type of machine. Another example is this beautiful metallic bunny, which is a beautiful shape for a movie, but it's a completely fictional shape in the real world, since a non-stretchable material like metal cannot physically bend into this shape. So instead, we proposed imposing priors on an object's curvature so that it can be built out of this type of material. This prior-aware modeling can even mean incorporating differential equations in the modeling process to guide the design to specific physical properties like heat or electrical conductivity. So this incorporation of priors into how shapes are created was one of the research directions I pursued, especially during the first few years of my research career. But another very related topic that I've been interested on lately is how we choose to represent geometry, the formats that we use to store geometric assets. In the entertainment industry, we usually want shapes that are easy to edit, easy to animate so that we can easily generate different sequences or versions of the same geometry. We also want them to be easy to texture so that we can draw any pattern that we want on top of them easily. We also want them to be easy to render, to take a picture of so that we can show it to a player or a viewer on a two-dimensional screen. These are the priorities of the entertainment industry, and the best way of representing a shape for all of them are the polygonal meshes that you might be familiar with. Triangle meshes, quad meshes, these have been the standard representation in our field for decades now. But that doesn't mean that polygonal meshes are the best for every application. For example, imagine that instead of for a Pixar movie, we want to represent a car because we're programming a self-driving car. In that case, we don't care that much about editing or texturing or animating the car talking or rendering the car. Instead, we care about other very critical questions. For example, when we plan a given trajectory, is the car going to crash against something or not, right? Is it going to collide with an object on the street or is it not? One way of answering this question would be to compute the region of space that is covered by the object as it moves along this hypothetical trajectory, which is something that mathematically is called the swept volume of the object, and then check if that swept volume intersects anything in the scene. And if it does, it means we're going to crash and we should look for a different trajectory. However, computing this swept volume given an object and a trajectory is a surprisingly rich and mathematically hard problem to solve. it's particularly hard to solve if we choose to represent the car as a polygonal mesh, which in 2 dimensions I am using in this example would just be a polygon. Computing the swept volume of a polygon along a trajectory would require looking at every edge of the polygon and analytically finding the edge's swept volume. This, you have to compute a very complicated formula, but it has a closed form solution, so it is possible. Then we'd need to discretize the edges sweep somehow, so that usually with another polygon, so that we can store it inside a computer. And we would need to repeat this for every edge, sweeping, discretizing, and as you can probably imagine, doing this for every edge will result in intersections. So all the time, we would also need to be resolving these intersections, a very computationally expensive process that can have even floating point robustness issues. And we would need to do this for every edge in the polygon, every segment in the polygon, and for every bit of what's potentially a very large trajectory. And that's just for this simple 2-dimensional car. If we wanted to do it in 3D, then we would have to find sweeps and do intersections for every polygon in the mesh, which is just computationally intractable. What this means is that we cannot effectively repurpose what is the standard geometric representation of choice for our critical robotics application of the self-driving car. People have tried this, by the way. This is not a straw man I'm making up, but using meshes means that they have to restrict themselves to very simple trajectories or very restrictive shapes. Instead, we'll need to go back to square one and think about what geometric representation is best suited for this task. I've proposed together with my colleagues that instead of as a polygon or as a mesh, we represent the car through its sign distance function. Sounds a little fancy, might be familiar to some of you who work on geometric machine learning, but this is actually a very simple concept. It just means that we represent the car not as a set of points or segments or anything like that. Instead, we represent it through a mathematical function that returns a scalar value for every point in this slide. So for example, at this point x here, it will return the function's value, which is the distance from x to the surface of the car. This function is defined for points outside the car, like this x, but also for points inside the car, like this y. And it's still the same thing, the distance from y to the contour of the car. To distinguish between inside and outside, we add a sign to this function, making points inside negative, or orange, and points outside positive, or blue. Now, in practice, if outside is positive and inside is negative, what it means is that the zero ISO contour, which is just a mathematically fancy way of saying the points that have value f equals 0, is just the surface of the car. Now, it might seem kind of counterintuitive or strange to represent a shape implicitly like this through a function without actually storing anything explicitly, any points on the shape, but this is a very useful representation. It's particularly useful in applications like ours, so let me show you why. Consider this point on the slide. As the car moves along its trajectory, the sign distance at this point also changes, giving us a function of time like the one that I graph here on the top right. This is a continuous function over a compact set. So if there are any mathematicians in the audience, you know that it has a global minimum. And this is true of every point on the slide, right? For any point on this line, I could have plotted this one-dimensional function. It would still be a continuous over a compact set, so it would still have a minimum. So I can plot the minimum for every single point on the slide, and then we would get this new function, which looks a lot like the sign distance function of the volume swept by the object, doesn't it? And we would get this function just by taking that minimum without having to do all that very invasive polygonal mesh surgery that I described earlier, simply by choosing the right shape representation in form of the sign distance function. In other words, it seems like sign distance functions are a very promising representation for this task. However, the path from one to the other isn't completely clear yet, and we'll need to answer a few research questions. Most importantly, okay, fine, that minimum gives us the swept volume, but how do we actually compute that minimum? Given a single point on the slide, how do we find the minimum of this plot? Well, we could do the most naive thing and sample the function at regular intervals and find the discrete minimum among them, but then we would get something like this, which doesn't look a lot like the real swept volume. And even if we sample more and more densely, in practice, it's still noticeable it's still noticeable that it's different from the real swept volume, and the difference between those two might mean that we miss some collisions of the car, right? Now, some of you might be thinking, and this is a machine learning series, so I imagine that a lot of you are thinking, gradient descent, right? This seems like a smooth function, so maybe I can start at some time and just follow the function's gradient until I find a minimum. And you'd be right, this could work, but if we choose the wrong starting point, then we could get stuck in a local minimum, in the wrong local minimum, which in practice manifests itself as missing entire components of the trajectory. So, uh, you know, I don't want to be grim, but like imagine all the children that are in that were standing by that middle part, right? We wouldn't find any of those collisions, which would be catastrophic, right? So this is a pretty hard problem, but fortunately we noticed something. If we consider 2 points on this slide that are close to each other, their sign distance over time function also look pretty similar, right? There's some continuity on this function space. Not only do those functions look similar, the time at which the minimum happens for both functions is also similar. So there's some continuity in the argument of this function, to be mathematically precise. So this is a pretty simple observation, but based on this simple observation, we propose a new algorithm, which is let's start from one point for which we know where the minimum happens, right? Let's say that we did a lot of computation just for this one point, and let's keep a record of where the minimum happened for that point. Then we move a little bit towards one side and look at a new point. The sign distance function at this new point will be a little bit different than at the previous one, but we can use the time at which the minimum happened for the previous point as a starting point and do gradient descent to find the new minimum. The fact that we're starting from the previous minimum and the functions don't vary a lot from one point to the other means that we avoid those problematic local minima. We do this for a new point, right? Using the point's previous minimum as a starting point, and we keep propagating this process further and further using the previous points now as the new sources for the points further away, doing gradient descent, and just propagating further and further from one point to its neighbors until eventually we fill out a whole grid of sign distance function values. Now, at the end of the process, we get samples of the function that represents the swept volume of the car. It might be hard to see here because in this didactic example, I used a very coarse grid, but if I make it finer and finer, you'll probably start to see the shape that we are now familiar with. This is basically the strategy that I proposed a few years back with my two co-authors, Noam Eigerman and Alex Jacobson. And it's in its simplicity, this strategy ended up being surprisingly robust to the input geometry. So as a stress test, we considered this very complicated shape, this Star Wars spaceship, which we can also assume, similar problem is planning a trajectory and it wants to know if it's going to crash or not. Well, we can compute its swept volume with no issue with our algorithm, and we can check that it does intersect that rock. So the spaceship should find a new trajectory. Now, we also found that this algorithm is very robust to the trajectory that the shape follows. I don't know how good this will translate over Zoom, but here we have a spin top that is rotating many times per second. It's inspired by the last shot of Inception, the movie, because my co-author Noam really liked that movie. It's a very complicated trajectory with many intersections, and nonetheless, we can compute its swept volume too without issue. And you can only imagine how hard it would be to compute this swept volume if we were using a triangle mesh to represent the spin top, right? We would need to solve all these tens of thousands or even millions of intersections on triangles intersecting each other. But we don't need to do any of that just because we chose sign distance function. So this is the work that we introduced in 2021. Unfortunately, it's only the first step to efficient swept volume computation using sign distance functions. It doesn't take us all the way there yet, since what I get at the end is a function. Well, not even a function. What I get at the end is just a bunch of samples of this swept volume sign distance function. But these samples are not what I actually want. Remember, what I want is the contour of this swept volume so that I can test if it collides against something, and I can see if my car is going to crash or not. But going from a finite set of SDF samples, like the one we produce, to the function zero level set or the function zero isocontour is far from a trivial task. And That being said, this is a room of smart people, so I think if I let you think for a few minutes about how you would solve this problem, you'll likely start thinking something like this. Well, there's 3 points at which I have a negative value, and there are many other points everywhere else where I have positive values. And remember, orange is negative, blue, different shades of blue are positive here. So if I look at an edge like this one, the function must go from negative to positive along the edge. It's a continuous function. So surely the function must take the value 0 somewhere in the middle. In other words, the zero level set, the zero iso contour, must cross this segment somewhere. And maybe through some linear or quadratic interpolation or something, I can make a more reasonable guess of where it will intersect, right? We can actually do this for every edge where the sign of the function changes and produce a reasonable guess for where the point, where the zero level set will cross each edge. And we can even link them using segments or some other way to get a guess of what the zero iso contour will look like. This method I just described is called marching cubes, and it's been one of the state-of-the-art algorithms in computer graphics for this specific task since many decades ago, right? Only recently improved by some much fancier neural approaches. Now, of course, those of you not familiar with marching cubes may be surprised to hear me say that this is a state-of-the-art algorithm, especially since the yellow curve looks nothing like the actual iso contour that we wanted to compute, right? So if I want to use SDF data reliably for critical applications like finding if a car is going to crash or not, we need a reliable way of extracting these iso contours. Fortunately, we did just that, and I'm going to show you a little bit about how we did it. We did it by going back to the definition of sign distance and thinking through the exact information that each sample gives us about that zero iso contour. For example, consider this point x. By definition, the value of the distance function at this point measures the distance to the contour that we care about, right? To put it differently, it's almost like if I drew a sphere around this point and I set the constraint that the contour has to be tangent to this sphere. This might sound fancy, but this is just what distance means, right? If you're a meter away from something, that means that if I drew a sphere of radius 1 meter around you, that sphere would be tangent to that thing, right? That's trivial. It's just what distance means. And we can do the same reasoning for every single sign distance function data point that we have, and drawing a sphere from it with radius, the magnitude of that point, and setting the constraint that the contour has to be exactly tangent to all these spheres. We can do it for all of them and get something like this. So now we can phrase the problem of reconstructing the contour as one of finding a curve that is tangent to every one of these spheres, which is exactly what we did to get something like this. Now, there are many, many details that I'm skipping over, but this is a strategy that we proposed in 2 recent publications with my colleagues Christopher Batty, Oda Stein, and Samara Ren, where we look at this problem of reconstructing contours from sign distance functions. And this is something we managed to do significantly better than the marching cube state of the art. And the difference is even more stark in 3D, where the shapes that we output with our method are much, much closer to the ground truth. In fact, I told you earlier that marching cubes isn't quite the state of the art because there are these much more fancy neural methods that have been proposed recently. Well, turns out our algorithm, which is based just on this geometric intuition, even outperforms those fancy, most recent neural algorithms that need huge data sets of thousands of shapes and dozens of hours of training time. I'll pause here for a second. I thought there was a nice moment to pause, right? So you can admire just how cool our algorithm is. In other words, we managed to compute contours from sign distance functions, which moves us one step closer to the goal, but not entirely just yet. Because in practice, I don't just want to compute one contour of one swept volume along one trajectory and see if we're going to crash or not. We ideally want to use the information to design a new trajectory, find a new contour, and hopefully validate that that one is not going to crash, right? So far, we would have detected that there was going to be a crash and we could maybe stop the car there, but ideally, we want the car to move along a different trajectory that is not going to crash. And ideally, I would love to do this without having to compute a whole new swept volume for every new trajectory that I consider. That would be so expensive. too expensive for a car to do it at runtime, right? When the car is running. Ideally, I would like to compute all the sweat volumes for all the possible trajectories of this car at once, right? If I could compute it once for every trajectory and then just store that and load it in the car, then when the car is considering a trajectory, I could just query that trajectory and see if it's going to crash or not. And if it's going to crash, I could just query a different one without having to compute a new sweat volume because I've stored all of those in the car already. This sounds a little bit complicated, but hopefully you can see that it's not as complicated as it sounds, because computing 9 sweat volumes is not 9 times as hard as computing 1, right? There is some regularity to this space that, even if I don't know how to phrase it mathematically, surely there is some regular structure to the space of all these sweat volumes. So this is a machine learning audience. If there's a regular structure that is hard to phrase mathematically, but I'm pretty sure exists, what should I do? Well, what if instead of computing one sign distance function of one sweat volume, what if we learned a whole latent space of sign distance functions, right? This is exactly what we propose doing in this recent work led by the amazing student Zoe Marshner, amazing student at Carnegie Mellon. By learning all the sweeps on this space, we end up with a parameterized model that contains in it all the possible trajectories that the car could take. Of course, a car is a very simple shape, but this is very robust to more complex 3D geometries like this spaceship, where the latent parameter measures the number of rotations along the sweep. You'll notice there's a lot of spaceships in my talks. That's my fault. Anyway, so this is the last piece of the puzzle. We can finally use sign distances for sweat volume computation efficiently, finally putting them at the same level as polygonal meshes are for entertainment. In fact, despite this very foundational work being very recent, we have already seen it applied by others to robotics applications like designing gripper shapes and optimizing robotic arm trajectories. So exploring these new representation is another broad line of research that I've recently pursued, because finding the optimal format to represent geometry is, needless to say, extremely useful in many applications. However, in other applications, you don't really get a choice for how the geometry is represented. Let's go back to the car, for example. In practice, the car doesn't have this beautiful representation, complete representation of the scene that it's traveling through, right? I mean, unless it's going around a circuit that it already knows, right? A real self-driving car driving along the street most likely is mapping its surroundings with a scanner as it moves along them, right? Something like that. So even in the best of cases, its representation of its surroundings looks something like this. And let's just keep the points in the inner walls for simplicity. This geometric format, a set of points in space, is usually called a point cloud in geometry processing. And very often, apart from the point, we can also use properties from the scanner and how the light is reflected and other things that computer vision people know how to do very well, to get something like the normal direction of the surface at each of the points in the point cloud, leading to what we call an oriented point cloud. This is not an easy thing to do. In that one sentence, I'm kind of skipping over an entire field. But in graphics and geometry, we usually like to pretend that the input is this oriented point cloud. So this is more a compliment to computer vision researchers, that they do this so well that we can pretend that this is our input, not meant as a dismissal of that entire field. So anyway, this our car cannot choose to use a sign distance function or to use a mesh to represent its surroundings. Instead, it has to use the information that is contained in this oriented point cloud to navigate the scene and to answer the most basic questions that a self-driving car needs to answer. The most basic question being, of course, is the car going to crash or not, right? Now, the obvious way of answering this critical question is to use a surface reconstruction algorithm to convert this point cloud into a complete continuous surface, and then test if that surface intersects the car or not. That's how I would do it a few years ago. That's probably how most people in the audience would answer this question if they were given this problem in a class or something. The most well-known of these surface reconstruction algorithms is called Poisson surface reconstruction. And if we use it on this shape, we get a reconstruction that looks like this. So let's put the car back in the frame. According to this reconstruction, it's clear that the car does not intersect the surface, right? In other words, the car is not going to crash. But is it? I think that's a pretty scary conclusion to reach, right? After all, it's not that Poisson reconstruction has some additional knowledge about the shape. It's seen the shape before, it knows the shape, it went to the shape and scanned more of it without us knowing. No, it has the same information we have, and the algorithm is just making a guess of what the surface may look like. But this reconstruction process of going from a point cloud to a complete continuous surface is very, very underdetermined. There are many surfaces that could have produced this point cloud. The original shape could look like this. It could look like this, like this, like this, or even like this, right? All of these surfaces could theoretically be the original shape. Then what reconstruction algorithms do is use some heuristic to decide between all of them. And while the car will not crash against some of these choices, it will definitely crash against others. So the choice of this heuristic is very, very important. So while a traditional reconstruction algorithm might choose one of these guesses and very confidently tell us that the car is not going to crash, reality might be that the car will crash something like 40% of the time. And needless to say, there is a huge difference between these two answers, right? Especially if you're the company that's designing the car, or if you or your loved ones are inside the car, you really want to capture this reality rather than the guess given by the reconstruction algorithm. I've proposed modeling this reality through what I call stochastic reconstruction algorithm, a concept that we introduced to our community of computer graphics through two recent SIGGRAPH papers. And by the way, this slide might make it seem like I'm saying that these traditional reconstruction algorithms are sloppy or irresponsible or something like that. Not at all. That's not my intention at all. These traditional algorithms are great for the entertainment applications that they were initially conceived for, right? So the classic examples you will see in all these papers are digitizing sculptures, right? Where your algorithmic priority is to produce an aesthetically pleasing guess of what the surface may look like, and you can always scan more of it if you have some uncertainty. The problem really only appears when you try to repurpose these algorithms for other safety-critical applications like ours. These new application realms have new algorithmic priorities, and that's the gap that our work seeks to fill. Here's how we did it. Instead of thinking of traditional reconstruction methods are using some heuristic to decide between all possible surfaces, we prefer to think of them from a statistical lens. I instead we say that these reconstruction algorithms use statistical priors to select what they think is the most likely output. Now that's just rephrasing the same thing, right? These priors can be more or less formal, they can be data-driven, or they can be very simple. For example, a classic one is, let's pick the smoothest shape that interpolates all the points. This is the prior used by Poisson surface reconstruction. Basically, this algorithm works in two steps. First, it uses the point normals to extrapolate a vector field. This is a vector field that I like to call as zero as possible vector field, meaning that sufficiently away from the point cloud, it will default to zero. Then it uses the finite element method to find a scalar function whose gradient is close to that vector field. The function looks like this, and its zero level set is the reconstructed surface. By the way, just because I mentioned my previous work earlier, I should mention here, this is not a sign distance field, right? This is not measuring distances. It's just another class of functions that is positive outside and negative inside the shape. That's why I'm plotting it differently without the iso lines and all of that. So this last step of using the finite element method might seem scary, but it's actually simpler than it looks. It just means you set up a grid like this, you evaluate the vector field on a grid, and then you solve a partial differential equation to get the scalar field. And this is the Poisson equation that gives the name to Poisson surface reconstruction. So this is the classic way that the algorithm is presented. You find the vector field, and then you find the scalar function, a scalar field whose gradient is the vector field. But from our statistical perspective, we realized that this intuition gives us more information. If we consider all possible functions, and all of the shapes described by them, we can say that a function or a shape is more likely the closer the function's gradient is to that vector field v. Then Poisson reconstruction can be seen as computing the mode of the distribution, the most likely of all the shapes. Recently, we formalized this statistical intuition to compute the whole distribution of possible reconstructions. We did this by first, instead of a vector field, we computed a whole normal distribution of vector fields. We did this through something called a Gaussian process that some of the machine learning people in the audience might be very familiar with. But first, implicitly, I'm just going to represent this as a 1D Gaussian. Basically, we find a statistical distribution that makes some vector fields more likely than others, and the mode of this distribution is the Poisson reconstruction vector field. Then we again use the finite element method, but this time to compute the distribution whose gradient distribution is v. This sounds harder than it is. In practice, this distribution is also Gaussian, and its mean and variance have analogous differential relations to the original vector field and scalar field in Poisson reconstruction. Getting these functions with the finite element method is also simple. All we need to do is we sample the distribution on a grid, and we solve two partial differential equations to compute the mean and the variance. In the end, we get a Gaussian distribution for this scalar field, meaning that at any point in space, we can query a mean and a variance, which fully determine, and any mean and variance fully determine a Gaussian, which quantifies the uncertainty we have about whether that point is inside or outside the reconstruction. As we move the point, we get a new mean and a new variance, which lead to a new Gaussian. This statistical formalism is useful for many applications. For example, we can, yes, compute the likelihood that a car will collide with its surroundings, like in the application that I used to motivate the work, but also for more traditional graphics tasks, like to repair an incomplete point cloud by using this probability to guide the sampling. We can also cast rays against uncertain shapes. This is to say, given a camera position and a direction, we can compute the probability that the ray will collide against the surface at different points along the ray. This might seem like a very abstract thing to compute, but it's important for a very specific application, which is that given several camera positions, we can score them based on how useful they would be for the reconstruction process, allowing us to choose the best next camera position among them, which is, of course, a critical question in scanning applications when you want to efficiently learn the most information about an object. Although this is not exactly the query that one usually cares about when you're scanning something, we don't usually just want to ask which camera position out of 5 possible camera positions is best. Instead, we want to ask which camera out of every infinitely many possible cameras is the best next view. Now, this might sound like a nuanced difference, but it is critical, so critical, that to address it, we had to resort to designing a new algorithm. In this new algorithm, we propose computing these exact quantities following the same two-step process. However, now, instead of doing the grid discretization and the partial differential equations and all of those things, we're going to stick with this differential perspective and instead use a neural network parameterized by some weights to find this distribution. The way we do this is very simple. We take these differential expressions and turn them into terms in a loss function, right? This is probably something that most of you are familiar with. This is a loss function that depends on the parameters of the mean and the variance. And then if we randomly sample the vector field distribution at random points now, instead of at a grid, we can update the network weight so that the gradient distribution matches the sample distribution at those random points. And we repeat this process for many epochs inside of a training loop. And we have an algorithm that converges to the same function as before, but without the need for finite elements and a grid, all of those approximations. This means, in particular, because we're using a neural network now, we can now no longer just compute the score of 5 cameras. We can also ask what the spatial gradient is of this score, which means that we can locally follow the next best camera position to find the globally next best camera. This means we don't need to sample many cameras. We can just sample a single one and follow its path to the locally best next camera position. And in fact, this neural extension of our algorithm that I'm not getting into too much has many more benefits than this and can be fully integrated into a scanning process from obtaining an initial reconstruction to finding the optimal next scanning positions and to scanning from them and efficiently fine-tuning the reconstruction using the new data. So anyway, this is what I've done in the past 5 years. What do I want to do in the future, especially now that I'm going to start a new job where I need to be able to answer to these things? In the future, I want to build on this success through multidisciplinary collaborations with researchers in these overlooked application realms, building algorithms that more closely address their needs. Of course, this is a broad career-spanning goal, but let me show you a few ways in which I plan to do this in the near future. For example, so far my work has set a theoretical groundwork for representing stochastic geometry, and we have even used this framework to answer basic geometric queries like the likelihood that a car is going to crash or where should I scan next, right? These are useful queries, but they're very basic geometric queries to geometry researchers because they effectively both boil down to asking, where is the geometry, which is the most basic question you can ever ask about a shape. In fact, the geometry processing pipeline goes much further than that, and I think incorporating uncertainty further along this pipeline can be revolutionary. We could do things like stochastic registration, combining multimodal representation of a scene in a way that accounts for the inherent uncertainty in the process. We could ask how to compute differential quantities about uncertain shapes for applications like computing the likelihood that a scanned object can be gripped or detecting defective elements in an assembly line. We could ask how to analyze shapes in a way that accounts for uncertainty, for example, to decide the likelihood that an object in a scan is a tumor or that an object in a scan is a pedestrian. Finally, there's a whole host of applications that will be enabled if we figure out how to solve partial differential equations on these uncertain domains, not just base shape correspondence questions, but also simulating uncertain physical systems that will tell us things like the likelihood that an object is safe or fragile, or that a gas or a fluid is propagated in a particular way. Solving PDEs on stochastic geometry is a long project on its own, but I think the answer to it will probably rely on combining insights from past work on stochastic PDEs and also more recent work from solving equations with Monte Carlo approaches, like the works that came out of Carnegie Mellon University recently. So building this complete stochastic geometry processing pipeline is perhaps the closest line of research that I want to do when I start my new lab. But there are other research ideas that I kind of have in the back of my mind that I thought I would end by pitching to you too. For example, while the stochastic geometry processing pipeline and any stochastic pipeline ends with computing the likelihood of an event, the story doesn't really end there. Instead, those likelihoods are then processed by someone who makes a decision based on them. Now, this is not a very safety critical example, but you can think of a surgeon deciding whether to make a cut or not, a driver deciding whether to grab a steering wheel from a self-driving car, or a voter decided who to trust when faced with uncertain information. In all these cases, the uncertain information has to be communicated to a decision maker, and this is far from a trivial task and involves investigating what exact statistical quantities matter in each application, as well as how to convey them to humans, which are known to not necessarily be the most rational actors when dealing with uncertainty. Finding the answers to these questions will require collaborating, probably with practitioners in each application and researchers in human-computer interaction too. Finally, in some cases, uncertainty can be a proxy for unfairness, and I think this is particularly true of geometries of work that deals with geometries of the human body, from airport scanners to human body and face modeling, or the ones used in medical imaging applications. And as I've already studied with collaborators in graphics and the social sciences, the choices that are made in these algorithms often present different kinds of biases. And I think identifying these biases by studying algorithmic uncertainty, as well as using that uncertainty to guide a fairer design process, is a very promising research direction. So anyway, that's what I've done and what I plan to do in the future. I thought I would end by telling you that if any of these ideas, especially these last ideas that I mentioned, sound fun or interesting to you, or if in your institution you know of any students that are close to graduating from grad school or undergrad that might find them interesting, I should also use this opportunity to plug that I'm recruiting graduate students and postdocs to start at my new lab in New York. So please go to this link if you're interested, or share this link widely for more information. Thank you very much for your attention.
Right. Thank you, Silvia, for the wonderful talk. Any questions?
Can you hear us?
I hear you, yeah.
I have a couple of questions. In the beginning, you were talking about this approach for the SDF to find like sweep volumes, right? And you were talking about this two minimum points that are kind of close to each other, right? If they're like spatially close, then the minimums are close to each other, right? You were doing like this gradient descent, right? To kind of find the like minimum, like updated minimum based on the starting minimum, right? Does this assume that this is like kind of this function, underlying function is like reasonably, so basically the derivative is kind of bounded, so it's like kind of it does not like kind of fluctuate too much. So why does it work?
Thank you. Great question. Yes, it assumes actually more than that. So we have a proof in the paper that if we can bound the derivative, which effectively translates as bounding the velocity of the shape. So there is a very intuitive understanding for it, and we can choose the width of the size of the step, let's say, or the width of the grid, to be small enough that with the maximum velocity of the shape along the trajectory, you can guarantee that that gradient descent will not leave the right minimum. But there is a much more difficult thing, which is that sometimes, even if you never leave the well of a given minimum, if you have two minima, the one that is the global one might progressively change. So in this argument, there are singular jump discontinuities that we cannot recover. What we do instead is we do this propagation. The way I sort of phrased it here for simplification, it's kind of like a one-off. You just propagate once. In reality, the way the method works is that we propagate this grid, and then when it wraps back on itself from the propagation, instead of just stopping because the new point would be populated, it asks, is my new minimum from this new propagation path better than the minimum I had previously stored at this point? And if so, it corrects itself. And we also have, I don't remember if a proof or a very intuitive explanation in the paper for how this self-correction will eventually get you the right SDF everywhere, even if that means that you have to sort of revisit some points a few times. I think even in the most complicated examples I just showed you, you never visit the same point more than 10 times. Great question.
Yeah, thank you. Can I ask another question? Another question that I have for the reach for the spheres, you show like great results, but what is the computational cost of the reach? Like marching cubes are fast, right? They're like,
yeah, great question too. So our method is much slower than marching cubes. Our method we show is more or less linear in the input size, which is the same thing you can say about marching cubes. However, it is still like the constant factors are still much larger in our method. So in practice, it is significantly slower. The way we like to think of this is that our method is good if you don't have access to the SDF sampler, right? So if you couldn't generate more points, then the example we think of is if you find the SDF data in a USB stick on the street and you have no idea where it came from, you're okay with spending a little bit more computational time if it gives you the best guess of what the surface might look like. Or one thing I'm very excited by that I know this is a machine learning audience, so you maybe you will revolt by me saying this, but I have this sort of vision that language modeling and computer vision are both transitioning to much more complicated neural network architectures, be it transformers or diffusion models or all these fancy things that I don't understand. And that's, we in geometry, in 3D, we usually say like, oh, we can't have those things in 3D because we don't have enough data, training data. And I think that's kind of wrong. I think also one of the reasons that we also cannot transition to those algorithms is that every time we need to process geometric information, be it training or output or for any other task, we need these cubic grids that are huge to run marching cubes on, for example. So if you're imagining in a future 10 years from now where we have transformers for 3D SDF data that take 1 minute for every time you want to query the SDF, but they are great at other things. In those cases where SDF querying will be very expensive, then you also prefer a method that can reconstruct with less information, even if it takes a little longer. Sorry, the cheeky way of saying this, when I get this question very often, your method is slower than marching cubes. I always say that's because marching cubes is throwing away 95% of the data that it gets. If you're reading a book and I'm reading a book and you're reading only 1 of every 10 pages, you're always going to read it faster than me, right? So the answer is, which one of us actually read the book, right? So that's how I like to, the cheeky way of answering the question is that one, but I also gave you the real one.
Oh, great. Last question, I promise. So what is
Don't worry.
Is there a, so basically, this was what you said was related to my next question. Basically, so what you're saying, my next question was like, basically, what is the, so in marching cubes, you have this like grid resolution, right? Which controls this kind of quality of the reconstruction, right? So what you're saying right now is like, basically that you kind of, you don't have this like this like reach for the spheres doesn't have this like kind of resolution parameter. It's kind of already like gives you kind of I don't know what is the mathematical relation, but there's like kind of more of a like kind of like more continuous than marching cubes with the like so basically, for example, if we have like infinite compute and we infinitely increase the resolution of the marching cubes, will we get this like the same result as marching spheres or not, for example? Or they like, does it make sense what I'm asking?
In the limit of resolution, if you can bound so basically, if you can always make the resolution infinitely finer than the highest frequency detail in the shape, then marching cubes converges. Like you will always approach the perfect solution with marching cubes and also with our method. The problem is probably you won't be able to run our method on such a big grid. So maybe this is your answer, maybe it's not your answer, maybe it's not your question, but we only use a grid because we're comparing to marching cubes, right? Like all of the intuition that I said about you drawing spheres from the points and setting the tangency constraint, that is completely agnostic to where the spheres are centered, right? So one other thing that we're excited by our work is that it opens the door to sampling, to storing the SDF data optimally at the, if you ask yourself, like, where should I store this data so that it contains the most information about the shape, that's where you would want to do it. If you're asking about, like, what parameter do we have in our method to set the quality the same way that you have in marching cubes, I think it's not true that the marching cubes grid length really is like related to quality in an intuitive way, because you can have a grid size that completely misses a feature of the shape, right? So in our case, you can also use the grid resolution that you input as a measure of quality in the same way that you do marching cubes. But I think this intuition of the spheres also gives you some more useful way of quantifying that. So for example, I would look at what is the total volume that is not contained in any sphere, and that quantity will tell me how good my will give me a bound on how good my reconstruction will be. And I think that's a That's going to be much better than the grid resolution for that.
Thank you.
Thanks. By the way, happy to chat more offline if that was interesting. If I didn't catch your question at the end.
I signed up.
Great.
Any more questions? I have a question of my own. In the Poisson reconstruction topic, you mentioned all these heuristics that people have applied to reconstruct surfaces in this underdetermined system. I'm guessing one of those heuristics is what Screen Poisson reconstruction did with this regularization term to get sort of more sharper details by incorporating the samples you already have. I'm thinking, more recent works that can incorporate richer priors while leveraging large-scale data sets, right? So what is the interplay between these methods and your method's ability to measure uncertainty, right? Like if I can install uncertainty by just learning from large-scale data. So if I get very sparse point clouds, I'll still be able to confidently say that this is the surface.
That's a great point. I think the answer is a little bit disappointing in that the specific strategy that we use for our work relies on you being able to place a simple analytical prior on the scalar function, which is a little bit disappointing, right? Especially if you're machine learning people, the kind of prior that you're thinking of is, I saw 10 million cars and I know exactly what a car looks like. I want to load this prior into the reconstruction so that when my self-driving car sees something moving at 80 miles an hour next to it, it can reconstruct it exactly the brand of car that it is, right? That's probably the ideal situation. I don't know how to incorporate uncertainty in that. I mean, of course, I know of ways that we could try. Like there's a lot of work on uncertainty quantification in general machine learning, in computer vision. I have some thoughts of how to translate it to graphics tasks like reconstruction, but the beauty of these Gaussian processes formulation that we came up with is that it doesn't require training, it doesn't require data, so it's much easier. You get a distribution at the end. We've experimented with other strategies, and I don't think we have quite figured it out yet.
No more questions. Thank you, Silvia, again.
Thank you.
Yeah, we have the fees who signed up for the one-on-ones. Sorry, we'll see you soon. Thank you again.
Cool. See you, everyone.
Bye.